Welcome to AI Journal Club, the digital pathology podcast segment where we take a closer look at the research shaping AI in pathology. This episode is one of our AI-powered summaries series, AI-generated deep dive into a paper worth your attention. It's curated from our weekly DigiPath Digest live stream that I run every Friday morning. I'm Dr. Alex Zhurav, and this is your shortcut to stay current. Let's dive into it.
Welcome, Trailblazers, to another edition of the Digital Pathology Podcast.
It is great to be here. We have a really fascinating deep dive into the source material today.
We really do. You know, usually when we talk about waiting for a medical diagnosis, there's this expectation of a sleek, highly efficient machine at work.
Right, like you give a sample, it goes into some high-tech lab, and boom, you get an answer.
Exactly. But when you step into the reality of a public hospital pathology department, especially in resource-constrained areas, that machine is often, well, it's running on fumes.
Yeah, it's just buried under a literal mountain of glass slides.
And behind every single one of those slides is a patient, sitting at home just agonizingly waiting for the phone to ring.
It's a heady burden.
Yeah.
But today we're looking at a framework that uses simulated AI data to solve that very real human bottleneck.
Yes, we are unpacking a Journal Club-style paper that was just published in the journal Clinical Breast Cancer in 2026.
It is a remarkable piece of research. I mean, it forces us to completely rethink how we approach systemic healthcare gridlock.
The paper is titled, A Deep Learning Framework for Automated Triage of Breast Cancer Biopsies in Malaysia. It's authored by Yudi, Kurniawan, Budi, Susilo, Dewi, Yuliana, Shamima, Abdul, Rahman, and Siew, Leong.
And to really grasp what this team has pulled off, we kind of have to look at the ground-level problem in Malaysian public hospitals first.
Right. There is a severe shortage of histopathologists.
Which is the core issue. Because of this shortage, the turnaround time for a breast biopsy result frequently stretches beyond 2 weeks.
Imagine sitting with that uncertainty for 14 days. It's completely unacceptable.
That waiting period is agonizing. But, the root cause of this delay isn't just a lack of doctors.
No,
it is the architecture of the queue itself. The standard workflow operates on a first-in, first-out model, or FIFO.
Ah, right. Good old FIFO.
And the structural flaw with using FIFO in breast pathology comes down to the underlying statistics.
No.
Roughly 70 to 80% of breast biopsies turn out to be completely benign.
So, wait, you have highly specialized pathologists spending the bulk of their day reviewing harmless tissue.
Exactly. They are bogged down looking at fibroadenomas, simple cysts, while malignant critical cases are trapped in the middle of the stack, blindly waiting their turn.
Okay, let's unpack this because the operational nightmare of that FIFO model is so clear if you put it in everyday terms.
I love a good analogy.
Imagine standing in a crowded emergency room, right? You have a severe life-threatening trauma and you need a surgeon immediately.
Right, a true emergency.
But you are stuck behind 80 people who are just there to get a Band-Aid for a paper cut.
Yeah, it sounds absurd when you put it like that.
And the triage system mandates that the trauma surgeon must personally clean and bandage every single paper cut before they are even allowed to look at your chart.
That is essentially what is happening in these pathology labs. The system completely lacks a sorting mechanism.
So obviously, building an AI system to act as that sorting mechanism sounds great in theory.
Oh, it does. But it hits a massive wall in practice. We call it the data paradox.
Right, because to train a deep learning model to accurately identify cancer, you need an enormous volume of whole slide images, or WSIs.
Exactly. But compiling perfectly annotated, digitized data sets in a resource-constrained setting is incredibly difficult.
Because of infrastructure limits.
Infrastructure limits and also stringent patient privacy regulations.
So you can't just scrape 10,000 real patient biopsies to train your algorithm.
No, you definitely cannot. And this is where the authors did something wildly innovative. They completely bypassed the physical data bottleneck.
They didn't use real patient slides at all, did they?
Nope. Instead of spending years navigating red tape, they used a generative AI tool called StyloGen2 to synthesize the data from scratch.
Synthesize it, like they generated completely artificial whole slide images.
10,000 of them. 7,000 benign and 3,000 suspicious.
I have to say, generative adversarial networks, GANs, are fascinating mechanisms.
They really are. The adversarial part is the key to how they work.
Right, you essentially have two neural networks competing against each other. One network acts as a forger, trying to paint a microscopic image of breast tissue.
And the second network acts as a detective. It compares the forgery against a small baseline of real tissue images.
And the forger just keeps tweaking its images, learning from every single rejection until the detective can no longer tell the difference between the computer-generated tissue and the real thing.
That's exactly it.
But I have to push back here on behalf of the trailblazers listening because the immediate reaction to this is usually pure skepticism.
Oh, absolutely.
They used fake images to train a medical AI. I mean, how can you possibly trust a diagnostic algorithm that was educated on algorithmic hallucinations?
What's fascinating here is how they mathematically proved the realism of these images before they ever let them near the triage model.
Okay, how do you prove that an image is mathematically real?
They measured the generated slides using something called the Freshead Inception Distance, or FID.
Yeah, FID.
Yeah. And this isn't just a basic visual check. FID actually measures the statistical similarity of the underlying features, the textures, the cellular boundaries, the architectural patterns between the real dataset and the synthetic one.
Oh, wow. So it's looking at the actual pixel-level distribution.
Exactly. The lower the FID score, the closer the distributions overlap. They achieved an FID of less than 25. Which indicates exceptionally high statistical realism.
But math is one thing, right? Human biology is messy. It's another thing entirely.
Which is why they didn't just rely on the FID score.
They tested it on humans.
They took these synthetic images and handed them over to 3 expert pathologists for a blinded review.
And what happened?
The pathologists gave the synthetic images a greater than 90% plausibility rating.
Wait, really? 90%?
Yeah. The GenAI recreated the morphological hallmarks of carcinoma so accurately that the trained human eye simply accepted it as real medical data.
That is wild. So by doing this, they completely solved the cold start problem. They generated a massive, hyper-realistic data set without risking patient privacy.
Or waiting for massive infrastructure investments. But, having flawless synthetic images sitting on a hard drive doesn't actually diagnose anyone.
Right. You still need an engine to actually look at them. Which brings us to the architecture of the AI itself.
Yes. They built the model using a convolutional neural network, specifically leaning on a pre-trained ResNet 50 architecture.
This is a classic application of transfer learning, isn't it?
It is. Instead of teaching an AI from absolute scratch, spending massive amounts of computing power, just teaching it what a straight line is, or how to detect a contrast edge, they use a shortcut.
They take a model that has already been trained on massive, broad data sets like ImageNet. It already knows the basic visual alphabet.
Exactly. The researchers just fine-tuned it, teaching it to apply that foundational knowledge specifically to breast tissue morphology.
Which is crucial because a digitized whole slide image is incredibly dense.
Oh yeah, we are talking about billions of pixels per slide. A standard neural network simply cannot ingest a file of that magnitude all at once.
It would just overwhelm the system's memory.
Completely crash it.
To understand how they solved that, trailblazers, imagine trying to find a specific tiny anomaly, say, a single cracked solar panel on a high-resolution satellite map of an entire city.
That's a great way to picture it. You cannot process the whole map in one glance.
Right. You have to break the map down into a grid and look at it piece by piece. In this framework, they broke the massive slide down into smaller patches of 256 by 256 pixels.
Viewed at 20 times magnification, yeah. But breaking the image into thousands of patches creates a totally new problem.
How does the computer know which patches actually matter?
That is where they implemented attention-based multiple instance learning, or MIL.
The attention mechanism.
Yeah, the algorithm doesn't just average out the findings of all those little patches, because most of those patches will just be healthy tissue or empty space.
So the attention mechanism actually learns to score the patches. It assigns a higher mathematical weight to the specific areas that look irregular or suspicious.
Exactly. It isolates the most critical regions and aggregates that localized information to make one definitive prediction for the entire slide.
So what does this all mean for the performance?
Well, on their synthetic test set, they achieved an AUC-ROC, the area, under the receiver operating characteristic curve of 0.984.
Wow. That is near perfect discriminative ability.
And the overall accuracy was 94.8%.
But honestly, an overall accuracy number can be a little misleading in a triage scenario, right?
It can be, yeah. The metric you really need to look at is the sensitivity,
Which came in at 96.5%. And in the context of a triage system, sensitivity is absolutely king.
That distinction is the bedrock of medical triage.
Because sensitivity measures the model's ability to correctly identify the true positives. It means the model correctly flagged 96.5% of the truly malignant cases.
Right. If you are building a system to sort a queue, false positives are annoying, but false negatives are catastrophic.
You absolutely cannot afford to let a truly aggressive cancer slip into the low-priority benign pile.
Never. If the AI is overly cautious and flags a few benign cases as suspicious, that is completely fine. The human pathologist will just review a benign case a little earlier than usual.
But missing a cancer breaks the entire premise of the system.
Which is why the system is operating exactly as it should as a hypervigilant gatekeeper.
But this is where the deep dive shifts from a computer science achievement into, like, a health economics revelation.
Yeah, because having a highly sensitive algorithm on a server is great, but it doesn't automatically fix a chaotic hospital.
You have to test how this algorithm interacts with the friction of the real world.
Staffing limits, scanner bottlenecks, random influxes of patients.
Right, but how do you test that without actually experimenting on a live clinical environment?
Build a digital twin. They use a methodology called discrete event simulation, or DES.
Utilizing a Python framework called SIMPy?
Yeah. They essentially built SimCity for pathology. They programmed a virtual laboratory and ran it for 250 simulated working days.
Pumping 5,000 virtual cases through it.
And the level of detail in this simulation is what makes the findings so incredibly robust. They didn't just assume a steady, even flow of cases.
No, they constrained this virtual hospital to mirror Malaysian realities. What was it exactly? 2 pathologists?
2 pathologists, 3 technicians, and just 1 scanner.
Wow. And they didn't just have cases arrive like clockwork either. They used statistical models like the Poisson distribution to mimic the chaotic, bursty reality of hospital admissions.
Where nothing happens for 3 hours and then 12 cases arrive at once.
Right. They also used log-normal distributions to model how long it takes a human pathologist to actually read a slide.
Which is super smart. A log-normal distribution is perfect for this because a reading time can't drop below 0, obviously.
But it can have a very long tail if a pathologist encounters an incredibly complex, confusing slide that takes 30 minutes to decipher.
It is a stunningly detailed virtual trial. They ran this simulation twice to compare the operational outcomes.
First, using the standard FIFO workflow.
Then, they ran it again, inserting their AI algorithm right at the front door.
So in the second run, the AI scanned every incoming case, taking about 3 minutes per slide.
And it instantly routed the suspicious cases to a high-priority queue and sent the benign ones to a low-priority queue.
The impact on turnaround time, or TAT, was massive. For the suspicious, potentially malignant cases, the diagnostic turnaround time plummeted.
From 7.24 days in the old FIFO workflow down to 4.47 days using the AI triage.
That is a 38.3% improvement in speed. We are talking about cutting nearly 3 entire days of agonizing, waiting for a patient who urgently needs oncology intervention.
If we connect this to the bigger picture, we do have to acknowledge the trade-off.
There's always a trade-off.
Right. In any queuing system, when you pull someone to the front, someone else gets pushed back. The turnaround time for the benign cases actually went up slightly.
Increasing from 6.53 days to 7.15 days?
Yeah.
But structurally, that is an incredibly acceptable trade-off. Delaying a benign diagnosis by half a day is a strategic win if it means catching aggressive cancers 3 days faster.
Exactly. A benign fibroadenoma is not going to metastasize in those extra 12 hours.
And the simulation proved that this pure AI approach was vastly superior to other methods.
They tested a simple rule-based triage system, prioritizing cases based solely on clinical high-risk flags from a patient's chart.
But that only reduced the turnaround time by 12.1%.
And a hybrid system reduced it by 29.4%. The pure AI triage absolutely dominated at 38.3%.
Here's where it gets really interesting, though. We spend so much time talking about the patient experience, but the ripple effect of this intervention completely alters the daily reality of the medical staff.
It's life-changing for the lab. By allowing the AI to effectively sort the workload, the simulation calculated the pathologist's workload actually fell by 22.5%.
That translates to saving 422 hours of specialist time annually.
In a healthcare system facing a severe specialist shortage, that number is just staggering.
Through pure efficiency, just by rearranging the order in which slides are presented, they effectively added 0.68 of a full-time pathologist to the staff.
Without spending a single dime on salary.
Those 422 hours can be redirected toward complex diagnostic challenges.
Or tumor board collaborations. Or simply mitigating the intense burnout that plagues the specialty.
It even impacts the physical footprint of the lab. The authors introduced a metric you almost never see in these deep learning papers.
Oh, the sustainability metric.
Yes, the green laboratory impact. The simulation showed a 15.2% reduction in region and slide consumption.
This happens because of how a backlog changes human behavior. In a chaotic, backlogged ecosystem, pathologists often order expedited deep-dive immunohistochemistry stains on massive batches of slides.
Just to clear the queue quickly.
Exactly, frequently wasting expensive toxic reagents on tissue that turns out to be benign anyway.
But by having the AI definitively sort the low-priority benign cases up front, the lab can batch process them with standard, highly efficient chemical protocols.
They reserve the expensive, chemically intensive diagnostic stains strictly for the high-priority, suspicious queue. It actively reduces material waste.
This all sounds like a perfectly orchestrated ballet. I mean, we are saving patients 3 days of waiting.
Effectively conjuring a new doctor out of thin air through time savings.
And reducing toxic chemical waste. But my immediate worry is that real public hospitals aren't perfect.
Oh, they are far from it.
We are looking at simulated data running through a simulated hospital. What happens when this hits the messy reality of a physical lab?
That is the critical limitation. And the authors are very transparent about it. The next step has to be real-world validation.
Because synthetic data is pristine by definition.
But in a real hospital, staining protocols vary from day to day.
Yeah.
Different brands of digital scanners have slightly different color calibrations.
And the specific histological features of the local population might present edge cases that StyleGAN simply never generated.
All of these physical variables can degrade an AI's performance.
Not to mention the IT infrastructure. The simulation assumes that the AI perfectly integrates into the hospital's aging computer systems.
Right, it assumes zero tech crashes.
Zero network latency, and perfectly formatted files every single time. If the algorithm takes 3 minutes to run, but the hospital's aging server goes down for 4 hours...
Your turnaround time advantage completely evaporates.
Exactly. The algorithm is only as robust as the physical network hosting it.
True. But still, the proof of concept is undeniable.
It is. So, to synthesize this deep dive for you, Susilo, Leong, and their team have essentially provided a blueprint for dismantling systemic bottlenecks.
By combining synthetic data generation with discrete event simulation, they have proven that an AI triage system can slash critical diagnosis times by 38%.
Cut pathologist workloads by 22%.
And save physical lab resources.
And the genius of it is that they proved the mechanics of this without waiting years for real-world datasets to be manually annotated and cleared by privacy boards.
They simulated the data, and then they simulated the hospital to prove the concept.
It's just brilliant.
This raises an important question, though, one that pushes this entire methodology to its logical extreme.
Oh, what's that?
Well, if an AI can be trusted to run millions of discrete event simulations to perfectly optimize a pathology queue, how long until we use these exact same frameworks to map out a patient's entire multi-year medical journey?
Oh, wow.
Imagine an AI running thousands of variations of a patient's surgery, chemotherapy, and radiation scheduling before they even walk into the oncology ward.
Mathematically locating the one pathway that minimizes delay and maximizes the chance of remission.
Exactly. The digital twin of the hospital is already here. The digital twin of the patient's future is the next frontier.
Now that is a thought to leave you with. Look at the processes around you this week. Where is your hidden FIFO bottleneck, and how could a little strategic sorting break it wide open? Keep pushing the boundaries of what you are learning, Trailblazers, and we will catch you on the next deep dive into the source material.
That's it for this AI Journal Club episode. If you want more like this, make sure you're subscribed to the Digital Pathology podcast. And come join us for the DigiPath Digest, our weekly live session. During these live streams, you can vote which paper becomes an AI deep dive. And if you're serious about digital pathology, grab my free book at digitalpathologyplace.com. This is the best place to start your digital pathology journey. Thank you so much for listening, and I'll talk to you in the next episode.